All right. So still loading. So please listen. Last lecture, we tried the Euler method with a step length of 0.5. And if you're not sure, I can restate what is the ODE or problem that we are solving. And this is the solution with a step length of 0.5. Now, same method, if we don't change the method, but make the step length finer, like make it 0.1, the solution I can compute. What I did was to do the work and provide it to you so that you can try experimenting with different step length values. You can try 0.2 or even make it even cruder like 0.7 and see how the solution changes. So if I take the solutions, say for example, the exact solution, which is this line, and then the solution we got with the Euler method with a step length of 0.5. So give me 1 second here, I'll update the legend with a step length of 0.5 and Euler with a step length of 0.1. Okay, and here is the exact. So I'll get rid of these lines. Okay. So this is our exact solution, kind of like the truth or target that we want to achieve. And here is a very low resolution or low accuracy method with a very crude step length. And as you can see that when you make the step length finer, it gets better. And like you were saying, if you make the step length even more finer, for example, if I change this 0.1 to 0.05, like make it even finer, you can see my solution will start to get better. But of course, I have to add more points because now I was just having a counter that went up to all the way here with a step length of 0.1. So I had to update that. So let me just go back to 0.1 here. So now we want to learn more techniques and put them on this chart. And at the end of it, we'll have several methods done with several resolutions of step length so that you can see how to choose a step length as well as a method. It's to put it as in a analogy, it's like choosing a car. It's not just about the car, it's also about who is driving. It's about any kind of instrument, it's not just about the instrument, it's about how you use the instrument. So a numerical method is not any different from an instrument. It's a tool to solve an equation, and how you use it also matters. Okay. So now let me give the screen a quick break. Okay. So let's just for those who are not sure which problem we were doing last time, I just want to write out the problem and then continue with higher order methods. So this is example 25.1. dy by dx equal to minus 2x cubed plus 12x squared minus 2x cubed plus 12x squared minus 20x plus 8.5 with the initial condition y at x equal to 0 is 1. So this is the problem we chose, and the Euler method is what dy by dx approximated as yi plus 1 minus yi divided by h. So that leads us to say yi plus 1 is yi plus f of xi comma yi multiplied by h. This whole right side is what I refer to as f of x, . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 . 。 . 。 . 。 . 。 . 。 So based on your understanding of numerical differentiation, you look at this. If I ask you to comment about what is the order of accuracy of this approximation, what will you say? You have it, say it. First order, right? That is, if you had a Taylor series, yi plus 1 equals yi plus dy by dx at I multiplied by h, d squared y over dx squared at I multiplied by h squared over 2 factorial, and so on up to infinity. So you are moving this here, bringing h down and approximating dy by dx. So since you brought h down, you would also divide this by h. So this is first order accuracy. O, or the order of magnitude of the error, scales with h power 1. So Euler's method is only first order accurate. Okay, Euler's method is first order accurate. So now there are a separate. So if you think about, I also mentioned this last time. Here is, let's say, xi, and here is xi plus 1. So this distance is h, and then the value of the function here, that is, you are told what is your ODE? It is dy by dx equal to f of x comma y. If you read this equation literally, what are we saying? We saying the slope at any point follows this function. So what we did was to take the current value, that is, we take this point, which is yi, and then calculated the slope, which is f of xi yi, and then multiplied that by h. So this is h times f of xi yi, and then we added this to y to compute the next value. So this is your y I plus 1. Okay, this is what we literally did. Now the true solution here, that is the solution here. So suppose it follows something like this. What you did was to either overshoot or undershoot the true solution, and you can fix this in many ways. Instead of taking such a large jump h, you can keep making the jump finer and finer, so that your approximation that the function between the 2 points is actually a straight line gets better and better. If you go really fine, any function will look like a linear in a very small interval, like a piecewise linear. Okay. Instead of doing that, what we can do here is, like we did for the integration schemes, we can try to divide this h itself into multiple segments, okay, and try to say, for example, I'm here. Instead of projecting all the way to here, what I'm going to do is project to a shorter distance, and then based on the local slope, project to another shorter distance, and then project to another shorter distance. That is the same h xi plus 1. I can divide this into n segments, where n can be one segment, 2 segments, 3 segments, 4 segments, 5 segments, and so on. That is, if you try to do that stepping in smaller steps within a step length, you can achieve higher order accuracy. And this concept forms the basis of what is called as the Runge-Kutta method, which involve using multiple approximations for yi plus 1 by dividing h into n segments. So each segment will have a length. Each segment will have a length or width, however you see it, of h over n. And if you refer to box 25.1, you can find a derivation for the second order method for n equals 2. The reason I'm writing a lot of text here is this derivation is not very useful for us. What is useful for us is to actually get a first order method, which we just did. This is a first order accurate method, which is very intuitive and simple to derive. Second, third, and fourth order methods, which are very accurate and very powerful to use. We will just learn those methods and do examples with them, with how to use them. Okay, so but this is the underlying concept. So I don't want to say that this is not useful or never worth learning, but I don't have time to do this in class. So I'm giving you where to start, box 25.1. And if you walk down that path, I would be happy to talk to you, but that's not something we will cover in the exam. We are going to do more problem solving than developing numerical methods. Okay.
Does it have a length of h over n?
Say that again.
The last sentence there, the
Have a length of h over n. Sorry, h over n.
Note page number box 1, 2, 25.
Sure. Let me tell you. So that would be page 731. Page 731. So I'm going to create some space. Okay. I'll remove these details. And I'm going to write the first method we saw is Euler's method, which is yi plus 1 is yi plus h times f of xi yi. Okay, and whenever I say f of xi yi, just remember I'm asking you to substitute x and y at point I into this function and compute a value, which is easy to do. Just do that and put it here. So it's a number that you can easily calculate. So then Pranikuta methods, or in short RK methods. Okay, we'll do n equals to second order, or what is popularly called RK2 method. This is section 25.1. This is section 25.3.1. Okay. So how does the method look like? yi plus 1 equal to yi plus h times a1 plus a2 k2. What is k1? K1 is the value of the function at point I, is f of xi comma yi, and k2 is the value of the function at xi plus p1h plus p1h comma yi plus p2h. Sorry, not p2, they call it q11 k1. q11 k1h. And the constants a1 plus a2 must add up to 1. These are constraints on the constants, and in a second I'll tell you what these constraints mean. A2 multiplied by P1 should be equal to half, and A2 multiplied by Q11 is equal to half. Okay. So see, there are two hats you can wear. You are a user or you are a developer. You are developing numerical methods and you go into the ground roots of how to start with Taylor series and build an approximation like this. That is a different level of knowledge. What we are users. You want a reliable numerical method to solve problems for you. And here is a method, and there are constants that appear here: A1, A2, P1, Q11. 4 constants appear here. And I have given you constraints, 3 constraints for 4 constants. Based on what you learned in linear algebra or linear equation solving, what is the situation? 4 unknowns, 3 equations. So how to develop a solution? How many solutions are there? No solution or infinite solutions? Infinite. How do you generate solutions there? It's not a trick question. You got the first part right.
Don't you have an initial guess?
See, you have 4 to solve for, but only 3 conditions, which means one of them is a free variable. So you can choose, say for example, you can choose a1 equal to 0 and solve the remaining. That means a2 equal to 1, which means p1 equals half, which means q11 also equal to half. You can make that choice. If you make a2 equal to half, which means, or a1 equal to half, which means a1 equal to half, which means p1 equal to what? 1, and q11 equal to 1. You can make any other choice. You can make, for example, a2 equals 1/3, which means a1 equals 2/3, and p1 equal to what? 3/4. 3/4, and q11 equal to 3/4. 3/4. So there are infinite choices that you can make, can't you? Right? You can make one. So each of them is a valid numerical method. It's a valid way to set up this numerical method. So now how do you pick a winner? How do you pick the best method? What condition or criterion will you use? Is it an English saying or an American saying? The proof of the pudding is in the eating. English meaning, is it British or American?
British.
Probably British. Okay. So you have a goal which is to solve this equation and you have candidate methods. Each of this is a method. So how do you now assess which is the best method?
Outside of the 3 requirements you already have,
I make one choice.
right?
You make one choice. We
Right.
both have competing methods. How do you select the better method?
Kind of depends on the problem.
You solve the problem with both the methods and see which gives you lesser error. Right? That's the proof of the pudding. Right? So you see which gives lesser error, number one. Number two, how many of you are aware of the word optimization? So what is optimization?
You make some data, you compare trial and error.
Not trial and error, it's still, there is a method to the madness, but it's not always trial and error. What is optimization?
Being the most efficient.
Optimization is typically selecting some conditions or parameters which will lead you to a specific goal, or you have to set the goal and you have to choose or make choices to get to that goal. Now, I'm asking you to make a choice. You choose one and you compute the rest. That is a choice you have made. So there are infinitely many choices or combinations that you can write down. Now, how do you select the better numerical method? It is by comparing the methods on the basis of the error they produce when solving test problems. Of course, that means a lot of work because there are an infinite number of methods. We don't have all day to try each method and decide one. So there are certain candidates which are common or which are popular, and I'll just put those candidates down. They all have specific names because people who did this work came up with it and it was named after them. So one point I want to emphasize here is when you derive a numerical method, sometimes there are free choices, which means it's a class of methods. When I say RK2 is not a single method. You can come up with your RK2, you can come up with your RK2, so can you, and everyone can, depending on what choices we make here. Okay. The other point is this second order method. Look at this equation. Yi plus h times a first term, which is one execution of the function, and then a second term, which is one more execution of the function. When you did the Euler's method, you just take the step length multiplied by one execution of the function, which is the local slope. So I want you to visualize on paper this equation and this equation. And when I say visualize, what I'm saying is, if I were to draw out x, y, here is xi, here is xi plus 1, here is yi. I literally have this as h, this as h times f of xi, yi, and then this is, of course, this is the slope. So this yi plus 1 is simply yi plus h times f of xi, yi. If you are good with geometry, you would agree with me on this. All I'm doing is taking this point and adding this length to say I've got this length or this level. Are we all together? All we did was to visualize this thing.
Yeah.
Right? If something's not clear, please say something. We can try a different way of talking about it. Are you clear with it? Yes. All right. So now look at this equation and first tell me how to think about this graphic. What is happening here? Suppose you pick this choice. Let's say you pick A1 equal to A2 equal to half, which means you are taking xi Okay, and then if A1 equal to A2 equal to half, what is P1? P1 is 1. And what is Q11? Also 1.
What's it called Q11?
Sorry.
What's it called Q11?
For that, we have to go through the derivation, and there's a very specific reason for it, which to get there, we have to go through the derivation. Okay. So when you say this P1 equal to 1, what is this? This is Xi plus H, and then Yi plus K1 times H. And remember, A1 equal to A2 equal to half. Now tell me, what does it mean geometrically? Take this equation and think what it means on the graph. Here is Xi. Where is Xi plus H? Here. This is Xi. This is Xi plus H. You agree with me on that? Just moving to the right.
Yeah.
What is K times, or what is f of Xi Yi? That is this slope. And that is evaluated at this point. Slope evaluated at point I. And then the slope evaluated at point I plus 1. That is here. So this is slope at Xi, and this is slope at, let's say, Xi Yi at Xi plus 1, Yi plus 1. Okay, I shouldn't say Xi plus 1, Yi plus 1. This is the slope evaluated at Xi plus H and Yi plus KH, or in other words, this point. Okay, and then you are taking the average of K1 and K2. That's what multiplying by half means. Average of the two slopes. So this operation is nothing but taking Yi plus H multiplied by average slope. Can I say that? I just took, I mean, when we talked about Euler's method, I am betting some of you might have thought in your head, why take this slope? What's wrong about this slope? Like, why should you just, what is so sacred about the slope at point I? Why not take the slope at point I plus 1? You can, and that would be a combination of A1 and A2 that you can pick. But the idea is here, by picking the weighting factor as half, we are getting an average slope. You can pick the weighting factors in many ways. You can pick A1 equal to 1/3, A2 equals 2/3, which will make P1 equals 3/4 and Q11 equal to 3/4. Average doesn't always have to be even average, it can be a weighted average. So this is weighting, this is giving more weightage to the, this is giving less weightage to point I and 2/3 weightage to point I plus 1. You can do 1/4 weightage, 3/4 weightage, you can choose the weightage, but the idea is, if you have a curve, let's say you have a point here, the curve is slowly changing. Here is I, and then here is I plus 1. If the slope is very strong here, and the slope is not as strong there, you might want to give this slope higher weightage. So you can use this to give more weightage to the point I plus 1 and lesser weightage to the point I, or vice versa. All right, very clever. We can do average slope, we can choose these free variables, but at the end of the day, how do I get a method to do my job? How do you select that? Which of from all these arguments, I gave you a problem. For this problem, let's say this combination works really well or works the best. For some other problem, let's say I have dy by dx equal to e power 4x times tan x. Let's say I have this problem. Will the same combination work, or how will I pick a good numerical method for this problem?
probably use some, we shouldn't be just using functions that for answer, we're just numerical value, we should probably be using, geometric function like tan, sine, cosine, etc.
No, the question is not really about this problem or that problem. The question is broadly about how do you select a numerical method for any given problem. Yeah,
You can get the second derivative of what you're working with,
okay,
and that would tell you at what rate your slope is increasing or decreasing. So if you see a high, I guess, acceleration, using that terminology, if you see a high acceleration, then you would know to put more weightage on the second slope factor. And if you see a low acceleration, then you put more weightage on the first acceleration.
you don't have to put higher weightage on all the derivatives or all the points. You can put them on the points I and not on the I plus one. Yeah, yeah, that makes sense. That is, you have to pay attention to what is your function. The message is, first of all, not every function is created same. You don't need very sophisticated methods for all the functions. If it's a very simple linear type function or quasi-linear function, you can get away with simpler approximations. The more complex this is, the more higher order methods you may need, number one. Number two, to my question about, all right, how do I select a method to do my job? Always you have to try to select the method based on a test problem which closely resembles your target problem. Do it like a assessment problem, get the error analysis done, estimate the error and think, okay, my error in the real situation could be this, could be approximately this, and I'm using this as justification. It's like this. If you are in the armed forces, you take rifle practice or you take shooting practice. There will be statistics kept on how well you shoot, like how many percentage hits versus miss, etc. But in the battlefield, nobody is keeping all those statistics. People are busy. So you are a qualified marksman because you did well in test conditions, and what your generals are hoping is that you would do as well in battle conditions. That is the analogy here. You try to assess your method in a problem that you can control, so that in a problem that you don't or you're not able to control, you still assume that okay, it will still do at least as good as it did in the test problem, if not worse. Okay. All right. So now I want us to implement this method to solve the same problem on our Excel sheet with the choices A1 equal to A2 equal to half, P1 equal to 1, Q11 equal to 1. So with these choices, I want you to implement this in your Excel sheet. And for those who are trying, I'm going to do this with you. So let's do this together. So a minute for you to write this down, and then we'll implement this. Okay, so if we are done writing this down on your notebook so that you can actually type it into your Excel and also help me. Okay, so this is my sheet for Euler method. I'm going to duplicate the sheet, okay, and going to modify this in order to create a new sheet for RK2 method. Okay, I just changed the name to RK2. We'll keep the step length. Okay, so here it's going to be Y RK2 with a step length of 0.5. The exact solution will not change. Only thing that's going to change is here. Okay, and to recall, what is your RK2 method? Yi plus 1 is Yi plus H times A1 K1 plus A2 K2. H times A1 K1 plus A2 K2. Okay, so for those who have their own programming style or way of doing things, you can do what you generally do. I'm going to suggest something for others who want some help. I will first create columns K1, K2. Okay, K1, K2. What is K1? K1 is the function executed at point xi, yi. So if you are dealing with so first point, there is nothing to deal with. That is part of the initial condition. So you don't have to solve anything there. When it comes to the first point, which is I equal to 1, or let's say we'll call this current or I. Okay. So K1 is the value of the function evaluated at 0.5 and whatever value of y. Oh wait, hold on. Sorry. When I'm trying to solve for this point here, the current is actually the previous line. So the current is actually this. Okay. So I have to evaluate K1 at x equal to 0 and y equal to 1. So what is the function here? What is our function? Minus 2x cubed plus 12x squared minus 20x plus 0.5. I'll tell that again slowly. Minus 2x cubed plus 12x squared plus 12x squared minus 20x plus 8.5. Thank you. So this K1 is evaluated at x equal to 0, y equal to 1. Of course, the function here does not depend on y, but you get the point. 8.5 is the value of the function at x equal to 0, y equal to 1. Just adding some notes here. All right. And what is K2? K2 is the value of the function evaluated at xi plus h and yi plus h times K1. Okay, I hope you wrote this down. Okay, and if I'm wrong, tell me. I'm just telling it from memory. So now, what is xi plus h? Which is the value which is xi plus h? So this is next or I plus 1. Okay, this is xi plus h. Xi plus h. So this value 0.5. So what I'm saying is for K2, you have to evaluate the same function at instead of 0, you have to evaluate it at 0 plus 0.5 or just at 0.5. Okay. So you want to type this is equal to minus 2 times 0.5 cube plus 12 times 0.5 squared minus 20 times 0.5 plus 8.5. So that is 1.25. I'll give you a minute to make sure you get these two, because if you do, that means you understand how this calculation is going. Sorry. Yeah.
What is y of RQ2 times H1?
Y is this one?
Uh,
No, I haven't done this. This is old calculation.
Oh,
So if it's confusing you, I'll delete it and populate it separately. This is not part of what we are trying to do now yet. That was the Euler method.
Yeah.
Yes,
Is for the Y's of RK2, so H equals what's on the, whatever this is.
oh yeah, sure. That's just a column name I gave. Don't neglect your programming. Exam 3 could be a take home. So I'm still thinking, yes.
behind the screen you wrote something different for K2.
Let me just check. K2 is f of xi plus h or f xi plus p1 h, p1 is 1 and yi plus q11 times k1 times h.
You just wrote it like that because P1 and Q11.
Yep. Yep. Right now, yes, for the variant we are trying, P1 and Q11 are 1. Okay, so you have K1 and K2. Do we all have it? Yes, no? Are you good? Okay. Can we move on? Is everybody having these two values in place? Yes, no. If it's a no, please feel free to tell me what's the problem or we'll try to fix it. Okay, I take the silence as yes. So then, what is my YRK2 method? That is like writing Y1 or YI plus 1, YI plus 1 is YI plus H times A1 K1 plus A2 K2. You know your H or you know your YI, which is this 1 plus H is 0.5, lock it with a dollar sign, multiplied by A1. What is A1? Half. That's the choice we made in the beginning. So that is 1 by 2 multiplied by K1, or actually let's put A1 here, half. Oops, sorry. And A2 is also half. So that you don't have to hard code it, I'll just put it as a formula. So YI plus H times A1, which is 0.5, lock it, multiplied by K1 plus A2, lock it, multiplied by K2. 3.4375. Try it and maybe do it and see if you get that value. Yes. You want me to scroll to the right?
Oh, no, just, yeah, the code of what you had for what you had.
Formula, the formula? Yeah. Yeah, that might be hard to see. What you want to do is, this is equal to, I'll write it out for you. So I can see it clearly, so I'll write it out as I3 plus F1 multiplied by H1 times G4 plus J1 times H4, and you have to put the dollar sign on or press F1, press F4 for this, this, and this. You know what the dollar sign means. You've all taken that computing class, so you know Excel, I think. One plus
Let's say J1 plus 4. and
J1 multiplied by H4. Yeah, sorry, I'll rewrite this. J1 multiplied by H4. Okay, I should use a brighter color. Okay, I'll use black. Have some of you been able to get the value 3.4375? Yes, those who are trying, Richard?
Yes.
Yeah.
1.4375.
Maybe you missed the weighting factor, or maybe you had a wrong weighting factor. See, this one step is what stands between us and automating everything that comes after us. If you get this, all we have to do is populate more rows, vary the step length, and convince ourselves that the method gets better as you make the resolution fine. You have it, Jeffrey? Good. 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 Can we move on? So before we move on, make sure that you put the dollar sign before F1. That is, you go to F1 and press F4. So, sorry, that's the wrong way to say this. So you have multiplied by F1, right? Before the parenthesis, the H value has to be locked. That is, for every value, you have to use the same step length. So ensure that. And if you are good with it, let's scroll it down. And the first thing that you should notice is that the percentage differences are actually much better than what we remember from Euler method. It's around 20% or thereabouts. If you go to the other sheet and looked at the numbers here, that is at least 50% or higher. That is, when you use the first order Euler method with a step length of 0.5, you get 50% error. And when you use the second order RK method with the same step length 0.5, you get around 20% error tops. Okay. Do you see that? You get different error, or actually, to put it more graphically, so here is Euler with 0.5. To this set, I'm going to add my RK method with the step length 0.5. Oops. Sorry, I did something. Please don't crash. No. Okay, now we just have to wait for it to calm down and not bail on us. So please try graphing it. That's my message. Try adding it to the graph. See how far we saved. Okay, good. So if I go to my chart, I'm going to add. Yeah. So I'm going to add RK2 method, okay, which I have here, edit, X values, Y values. Oops. Okay, y values. Okay, all right. Okay, so please stop whatever you're doing. Look at this. This line here is the Euler method with step length of 0.5. So this is Euler method with a step length of 0.5. This here is RK2 with the same step length. So a higher order method gets you better accuracy with the same computational effort than a lower order method. So in general, higher order methods are preferred. Why? Because they lead to better accuracy. Like I said about always using the error metric for selecting methods. But the higher order method also has more operations. Did you realize that when you did the Euler method, you just had to execute the function once. Now you had to execute it twice. So it comes with a slightly higher operation cost. But that is okay because you are still getting better accuracy. So now what you can try is we can go more finer resolution. You can take 0.1 and you will see what you can almost tell what the trend is. As you make this 0.1, the true solution will be better approximated or calculated by our numerical method. So you can do that, as an activity. I'm giving you this Excel file so you can play with it around. Try to use different step length and see how the accuracy changes. What we are going to do now is to learn after this RK3 and RK4 methods, third order and fourth order. In fact, it goes on. There is RK5, sixth order methods and so on. We'll stop at 4 because at one point what happens is you get better accuracy with these RK methods, but they also have a lot of operations that you have to execute the function 6 times or 7 times at each time step. From a computing point of view, that becomes very laborious. So we just stop at RK4. Okay. So giving you a minute here to wrap up things with RK2 and ask me if something isn't clear.
You show your formula for K2 because like all my values after the first one are wrong.
Okay, that is just executing the function at this x value here. So this row is current, this is next. When you go to the next row, this becomes current, this becomes next. So K2 is based on this row, K1 is based on the diagonally previous.
Can you show the formula in this form?
K2?
Yeah.
Okay, maybe it's not. I don't think I can zoom that line. Let's see if I can do a screenshot and put it for you. So is everyone able to, those who have their Excel and trying this, are you able to get this solution, graph it, and convince yourself that RK2 method gets you better accuracy?
Yes.
Okay. All right. So now we want to go back to the whiteboard and learn the RK3 method, that is learn the formula for RK3 method. Yes.
Not for this memo on my Excel, but it's setting every value to 0 after I put in the formula.
Maybe you forgot the dollar sign.
Well, no, like I'll write equals 1 plus 1 and it'll just return 0.
Yeah, I don't know maybe it's definitely not related to the numerical method. So let's all right, so we saw RK2 method. Okay, so I'm going to take that and write it here. Yi plus 1 is yi plus h times a1 k1 plus a2 k2. Okay, and you know what k1 k2 are. So if you are preparing for your exams, you want to know this formula. You want to know this formula, that is not these choices. You want to know this formula, and then I will say either choose your own numerical method, in which case you have to actually make a choice and compute P1, Q1 and use it, or I will say use A1 equal to half or 1/3 or whatever. So you should know it at the level of the constants appearing in the formula. Okay. All right, so now maybe we'll leave it like that and learn the RK3 formula. So RK3, conceptually speaking, it's just dividing the segment into 3 pieces and then getting a weighted average of them. So you can write RK3 yi plus 1 is yi plus h times sigma I, maybe I'll write j equal to 1 to 3 aj kj. aj kj. Okay.
That's 3 on top of the summation.
Yep. J, the index j runs from takes values 1, 2, and 3. A1, K1, A2, K2, A3, K2.
Anyway, just because in this problem we're going. Or is that just, oh, no.
Say it again.
So that's just, is that a constant for?
For this RK3 method. For RK4, it will become 4. In fact, you can generalize all of the methods as j equals 1 to n, where n is the order. All right. So what is aj, kj? What are those values? A1 is 1 over 6. A2 is 4 over 6. A3 is 1 over 6. So the book is just presenting to you a very common variant, not the only possibility. 4 over 6 or 2 over 3, and A3 is 1 over 6. Okay, and K1 is f of x comma y. The K1 is still the same. K1 is f of xi comma yi. K2 is f of xi plus half h plus half h or h over 2 and yi plus k1 times h, think k1 plus h, k1 h over 2 and then k3 is f of xi plus h and yi plus k2 times h. Yi minus kh plus 2k2h. Yi minus k1h plus 2k2h. And while we are here, even though we haven't done an example yet, or we haven't implemented this yet, might as well see what is RK4. So A1 equal to A3 equal to 1 over 6, A2 equals 4 over 6. So this is all of RK3. Okay. RK4, yi plus 1 equal to yi plus summation j equals 1 to 4 aj kj multiplied by h.
Wait, so can we have a K4 value?
for RK4, not for RK3. Yeah,
Are those A1, A2, and A3 values always gonna be the same?
good question. This is a variant, not any, like, there are many possible choices. The book just gives you one choice, not to confuse us. Let's stick to it. So for your exam, if I say RK method, you can just refer to this method and use it, and RK3 method. that is. A good problem in the exam will not test your memory. I won't try to trick you by saying, got here, instead of 2/3, you use 1/3, here you lose 30 points, nothing like that. I will just give you the method that you have to use and try to put some other question that will test your understanding. That's what I'm supposed to try. Because I had terrible instructors back in India who did exactly that, and when I actually went and explained to them that I understood what's going on, but I just missed this, I always got very poor grades. But that's when I understood that I understand this stuff better than these guys, and I can become a teacher. So, all right, your values for the coefficients. So A1 and A4 is 1/6. A1 equal to A4 equal to 1/6. A2 equal to A3 equals to 2/6. And K1 still remains the same. K1 is f of xi yi. Okay, it's going to be a little tricky. Pardon my poor organization skills. I'm going to put this here. RK3 yi plus 1 equal to yi plus j equal to 1 to 3 aj kj. Okay, this is RK4. Okay, let this be here. So I'm just going to continue writing about K2 here, K3, K4. So K2 is f of xi plus half h, f of xi plus half h, and yi plus k1h over 2. Are you ready, Al Hassan? Yeah, I'm ready. Okay, 5 more minutes. And then K3 is half h plus half K2h. F of xi plus half h plus yi plus K2h over 2. All this is in the book, so maybe if my handwriting isn't clear enough, I'll tell you the equation numbers as well. And then f of xi plus h comma yi plus k3 times h. This is RK2, RK3, and then Euler. So RK4 is equation 25.4. Equation 25.4. RK3 equation 25.39. Oh, it's 25.40. 25.39. Equation 25.39. 39 And then second order method, the most general form is equation 25.30. I think that is 40. So standing instruction for you, now that you know how to do the implementation of RK2, stretching it to 3 and 4 is not a big leap. You can implement RK3 and 4 on your Excel sheet and be ready. Okay. I will connect using that implementation to homework 5. That is, we are going to have 2 problems for homework 5. If you have your code working and ready, I post the problem. You can just solve that in like 10 minutes, literally. So I will post the homework probably tomorrow, but I want you to build this code and be ready. Okay. We might ask you to upload your Excel files, and trusting you're all good people, you won't take your friend's Excel file and upload it. I'm assuming you'll all do your own work and upload your work. You're not engaged in any inappropriate collaboration. You can talk to each other, but just don't literally copy. Okay. So what remains is for us to do examples and also discuss about what is the way to estimate the error when you use this numerical method. Mainly we have seen only one problem, so we want to see more examples, which I might either do next Tuesday or I might do that as a recitation session, but I don't want to do recitation. I want to actually tell this to the entire class. So maybe next Tuesday we'll try to spend just doing this and word problems. Okay. And then one more announcement. After next Tuesday, there are only 3 more lectures remaining. There is one on Thursday, one on the Tuesday of Thanksgiving week, and then one when we come back from Thanksgiving. After that, study day will be here. So to go through module 3 or module 6, the last one, I actually don't have enough time or as much as I want. We have only 3 lectures, and I also have to accommodate exam 3 in those lectures. So instead of having a in-class exam, I'm thinking of a take-home exam for exam 3, which will be like you'll be given the same 4 problems, but 24 hours to work on it. So it will be posted on, let's say, Tuesday afternoon, and you'll have until Wednesday afternoon to bring a paper copy of the solutions and give it to either me, TA, or the ME office. Will collect the exams. So instead of an exam, you'll have 24-hour take-home exam. The other thing that I want to ask about is if I record, say I want 4 lectures to do statistics, I have only 3. If I record a 1.5 hour lecture and post it over Thanksgiving and ask you all to view the recording and treat that as the 4th lecture, would that be acceptable, or would you prefer cutting some topics out or try to squeeze it in 3 instead of having 4 lectures? Ladder meaning? I know what ladder means, like which option?
Cutting out.
Cutting out topics?
Yeah.
I didn't expect this from you. I thought you would say, sure, then we'll watch the video.
Look, I probably wouldn't, like, you could post it, I probably wouldn't watch it. I'm just being honest.
Yeah, thank you for that. All right, I'm still undecided, but exam 3, 99% is going to be a take-home exam, not an in-class exam, okay? And now he will distribute exam 1.
I admire. Yeah, we got.